We're talking about a massive shift in computing, like a fundamental change. We're moving way beyond the digital world we all know, into stuff that used to be pure science fiction. Think about it. The very idea of what a computer is changing, expanding from the little silicon chips in our phones to, get this, the actual proteins inside our own cells. And this question, this is really at the core of what we're talking about today. It kind of flips our whole perspective on technology on its head. Are we really inventing something brand new? Or are we more like, archaeologists, just digging up a language of computation that's been woven into the fabric of the universe this whole time? The answer? Well, it's probably not what you're expecting.
Okay, so to really get where this is all going, we need to start with the basics. The fundamental building block. In a regular computer, you have a bit. Super simple. It's either a 0 or a 1. That's it. But a quantum bit, a qubit, is a whole different beast. Thanks to this wild thing in quantum mechanics called superposition, it can be a 0, a 1, and both at the same time. It's not one or the other, it's yes, and that yes opens up an absolutely massive, almost unimaginable space for doing calculations.
So, let's get into the first part, the quantum race. And believe me, it is a race. Trying to build a quantum computer is one of the biggest engineering challenges humanity has ever taken on. We're talking about pushing physics to its absolute breaking point. It's a global sprint to build these machines that work based on rules that, they just don't make sense in our normal, everyday world.
And what's so wild is that nobody's agreed on the one right way to build a qubit. It's kind of the Wild West right now. As you can see here, people are trying everything. Some are using lasers to trap individual atoms. Others are zipping charged particles around these tiny little racetracks. You've got teams using particles of light. And of course, the big players like IBM and Google are engineering these super specialized circuits. It's a huge, simultaneous experiment.
But here's the massive catch. The number one problem is that qubits are, they're ridiculously fragile. These might be the most sensitive things we've ever tried to build. To get them to work at all, you have to completely isolate them from everything. A tiny magnetic field, a random bit of radiation, even someone walking by too heavily, poof, the whole calculation is gone.
And when I say isolate, I mean it. We have to create these insane environments to keep them stable. We're talking about cooling them down to nearly absolute zero. That's minus 459 degrees Fahrenheit. To put that in perspective, that is literally colder than the Boomerang Nebula, which is the coldest spot we know of in the entire universe. That's what it takes. This whole problem has a name. It's called decoherence, and it's the ultimate villain in this story. It's basically the universe trying to look at the quantum state. Any little interaction with the outside world, a bit of heat, a stray vibration, and the quantumness just collapses. It's gone. The analogy on the screen is perfect. It's like trying to balance a marble on the tip of a needle during an earthquake. That's why this is so unbelievably hard. Okay, so we've established this colossal problem of decoherence, right? Billions of dollars, decades of work, all trying to solve this one thing. But what if? What if the solution has been staring us in the face the whole time? This is where the story takes a really fascinating turn.
Yeah, what if the hardest problem in quantum computing was already solved, billions of years ago? What if the best quantum computer isn't in some super-cooled, shielded lab, but it's been all around us, and even inside of us, all along?
Just look at this comparison. It's just mind-blowing. On one side, you have the man-made lab, freezing cold, a total vacuum, shielded from everything. And on the other side, a living cell. It's warm, it's wet, it's buzzing with electrical noise. It's a complete mess. It's the exact opposite of what we thought we needed. For decades, scientists said no way could quantum effects survive in there.
Well, guess what? They were wrong. That whole assumption just got thrown out the window.
New research has found that inside the scaffolding of our cells, these things called microtubules, there are networks of proteins that are actually doing complex quantum computations. They're all working together as one big quantum system. It's incredible.
Okay, let's try to wrap our heads around how fast this is. Think about how your brain works right now. Your neurons are firing away, right? They do that about 1,000 times every second. Pretty fast, right? That's the classical speed of thought.
Now get ready for this. The quantum processes happening inside those very same cells are clocking in at 10 trillion operations per second. That's not just a little faster. That is 1 billion times faster. We're talking about computation happening at pretty much the absolute speed limit allowed by the laws of physics.
So what does this all mean? It means that nature already figured it out. It solved the decoherence problem that has our best scientists completely stumped. It's running stable quantum computations in a warm, wet, messy cell. It's like this researcher from Oxford said, nature found a way for us. And this discovery of nature's quantum secret is leading to a totally new way of thinking about computing. A third way forward. Instead of fighting against all that noise and randomness and chaos, what if we just used it? What if we leaned into it?
Think about it. Our current AIs, they run on chips that are designed to be perfect and predictable. But to do anything creative or solve hard problems, they need randomness. So we spend a ridiculous amount of energy forcing these perfectly orderly chips to act random. It's like the quote says, using a chainsaw for surgery. It's just the wrong tool for the job.
So this new idea leads to something called a p-bit, or a probabilistic bit. And the concept is brilliant in its simplicity. Instead of trying to stamp out the natural randomness in a transistor, you use it. You take that jittery, random motion of electrons, that thermal noise, and you turn it from a bug into a feature.
Here's how it works. You basically just dial down the power to a regular old transistor. When you do that, physics, the natural chaos, takes over. The transistor just starts flipping randomly. And when you link a whole bunch of them together, the whole system just naturally finds the easiest, lowest energy way to arrange itself, which, it turns out, is often the best solution to a really complex problem.
And the payoff for this approach is huge. We could end up with a totally new type of computer, a thermodynamic computer, that doesn't need any of that crazy cooling stuff. It would run on normal silicon at room temperature and could be up to 10,000 times more energy efficient than the best GPUs we have today for running AI.
Okay, so let's put it all together. What happens when all these different ideas, our man-made quantum machines, the discovery of biological quantum computers, and this new thermodynamic approach, what happens when they all start to merge? We're not just talking about one new thing anymore. We're looking at a great convergence.
And this isn't science fiction happening decades from now. The timeline is speeding up like crazy. We're talking about the next few years. IBM thinks we'll see a quantum computer beat a classical one on a real problem by 2026. Soon after that, you'll see these new technologies starting to have a huge impact on everything from discovering new drugs to designing new materials.
But really, the biggest story of all is when AI and quantum computing finally come together. And this is key. It's not just about making AI faster. It's about giving AI a completely new playbook, one based on the actual rules of the universe. The result isn't just going to be a smarter AI. It's going to be a totally new kind of intelligence, something that can think in ways we can't even imagine right now.
Which brings us to one last big idea to chew on. What if computation isn't something we humans invented? What if it's just a fundamental part of reality itself? I mean, we're seeing it in the quantum dance inside our own cells and in the physics of a simple chip. So maybe we aren't building the next great intelligence. Maybe we're just finally learning how to speak the language the universe has been speaking all along.